everyone, today we study Calculus 2. Double integrals over rectangles. Firstly, we will introduce the problem introduction. What is the volume of the curved top cylinder? Let's review the method. How to calculate the volumes of a flat top cylinder and a cuboid. The volumes of a flat top cylinder and a cuboid are equal to bottom area times height. Then, how to calculate the volume of the curved top cylinder? Below the surface, Z equals fxy, and above the region D. In fact, the method of dividing, approximating, summing, and the limit is used to obtain the volume of the curved top cylinder. Now, let's analyze the 4 steps in details. Step 1. Divide the bottom of the curved top cylinder and take a typical small area delta sigma I. Step 2. The volume of each small curved top cylinder corresponding to delta sigma I is approximately represented by a flat top cylinder. That is F cos I at I times delta sigma I. Cos I delta I is an arbitrary point in the bottom area delta sigma I. Step 3. Sum the volume of all the small flat top columns to approximate the volume of the curved top cylinder. Step 4. When the largest value of all the small area delta sigma I from 1 to 10 tends to 0, the limit of the sum is equal to the volume of the curved top cylinder. Pay attention to the fact where lambda means the largest value of all the small area delta sigma I from 1 to 10. Now we consider another problem in physics, the mass of the flat sheet. Suppose that there is a flat sheet that occupies the closed area D on the XY plane. The surface density at the point xy is ρxy. Assume that ρxy is continuous on D. Then what is the mass of the flat sheet? Here we still can use the method of dividing, approximating, summing, and the limit to solve the problem. Step 1. The flat sheet D is divided into small pieces. Take a typical small piece delta sigma I. Step 2. Approximate the mass of delta sigma I as a uniform thin sheet. That is ρ cos I at I times delta sigma I. Cos I at I is an arbitrary point in the delta sigma I. Step 3. The mass of the flat sheet D is approximately equal to the total mass of the uniform thin sheet. Step 4. Limit the sum, which is the mass of the flat sheet. Capital M is equal to the limit of the sum of ρ cos I at I times delta sigma I is from 1 to 10. Here, lambda means the largest area of all the small pieces, delta sigma I from 1 to 10. Notice that the volume of the curved top cylinder and the mass of the flat sheet depend on the same type of limit, the sum limit. Leaving aside the background of the problems, we study this kind of limit, which is the concept of double integral. Now we give the definition of double integral. Assume that f(x,y) is a bounded function on the bounded closed region D. The closed area D is arbitrarily divided into n small closed area, delta sigma 1, delta sigma 2, till delta sigma n, where delta sigma I represents the ith small closed area. Arbitrarily pick a sample point Xi at I in each delta sigma I and calculate the product of Xi at I and delta sigma I. Then calculate the sum of all the products on n small areas. Finally, calculate the limit. If the limit exists, we call it the double integral of xy over the closed region D. That is, the double integral of xy over the region D is equal to the limit of the sum of Xi at I times delta sigma I from 1 to 10. Here, D is the domain. f(x,y) is the integrand. xy are variables. f(x,y) times delta sigma is the expression. The sigma is the area element. This is the sum. There are some instructions that we should pay attention to. 1. The division of the closed region is arbitrary. 2. When f(x,y) is continuous in the closed area, the limit of the sum in the definition must exist. That is, the double integral must exist. In the rectangular coordinate system, the area D is divided by straight line network parallel to the coordinate axis. The area element D sigma is equal to ds dy. So, the double integral can be written as this. Now we see the geometric meaning of double integral. Recall that if f(x,y) is greater than or equal to 0, the definite integral of f(x,y) in the interval AB represents the area of the region below the curve y equals f(x,y) with x from A to B. In a similar manner, if f(x,y) is greater than or equal to 0, the double integral of xy on the region D represents the volume of the solid below the surface z equals f(x,y) and above the region D. What conditions does the function need to satisfy if it is integrable? Let's see the following integrability theorem. If f is bounded on the closed region D, and if it is continuous there except on a finite number of smooth curves, then f is integrable on D. In particular, if f is continuous on all of D, then f is integrable there. What are the properties of double integral? We assume that the functions involved are integrable in the given region. K is a constant. The double integral of k times f(x,y) over region D is equal to k times the double integral of xy over region D. That is, the constant k can be mentioned outside the integral sign. The double integral of algebraic sum of fxy and gsy over region D is equal to the algebraic sum of the double integral of fxy over D and the double integral of gsy over D. These two properties are called the linear properties. Additivity. Let region D be divided into two parts, D1 and D2. Then we have the double integral of xy over D is equal to the sum of the double integral of xy over D1 and the double integral of xy over D2. The double integral of instant 1 over region D is equal to the area of the region D. Here 1 can be omitted. Comparison. If fxy is less than or equal to gsy over region D, then the double integral of fxy over region D is less than or equal to the double integral of gsy over region D. Especially the absolute value of double integral of fxy on D is less than or equal to the double integral of the absolute value of fxy on D. Evaluation theorem. If fxy is greater than or equal to small m and is less than or equal to capital M over region D, sigma is the area of region D. Then we have the double integral of fxy over region D is greater than or equal to small m times sigma and is less than or equal to capital M times sigma. Middle volume theorem. If fxy is continuous on the closed region D, sigma is the area of region D. There is at least one point Xi eta on D that satisfies the double integral of xy over region D is equal to f Xi eta times sigma. Next, let's give some examples to grasp the above properties. Example 1. Please estimate the value of the double integral of e to the power x squared plus 1 squared over D, where D is the ellipse region. The square of x over the square of a plus the square of y over the square of b is equal to 1. According to the evaluation theorem, we need to estimate the range of the integrand on the region D and calculate the area of D. The area of D is equal to AB pi. As to D, because the square of x plus the square of y is between 0 and the square of a. Hence, we have the result. E to the power x squared plus y squared is between 1 and e to the power a squared. According to the evaluation theorem, we have the double integral is greater than or equal to sigma and is less than or equal to sigma times e to the power a squared. Namely, we can obtain the double integral is greater than AB pi and is less than or equal to AB pi times e to the power a squared. We continue to study example 2, estimate the value of the double integral of 1 over the square root of x squared plus y squared plus double xy plus 16, where D is a rectangular area. X is from 0 to 1 and y is from 0 to 2. the area of D, sigma is equal to 2. Last, we estimate the range of the integrand on D. It is obvious that the integrand is transformed into this expression, 1 over the square root of x plus y all squared plus 16. The maximum value of xy on D, capital M, is equal to a quarter when xy are both equal to 0. The minimum value of xy on D, small m, is equal to a fifth when x is equal to 1, y is equal to 2. So the double integral is from 2/5 to 2/4. This class we study the definition of double integral, integrability theorem, properties of double integral. Try to understand and master the above knowledge. Thank you. See you next time.